Our DC drive equipment can have different voltage supplies. To be capable of operating in different voltages, we sometimes have to have a dual voltage field motor. Dual voltage field motors have an F1, F2, F3, and F4 connections, and the fields are split apart into two circuits. For a high voltage field supply, we could series the coils, and for a low voltage application, we can parallel the coils. Here's an illustration of how a dual voltage motor would be wound and wired out. F1 would go out through these coils and back to F2. F3 would go back and return out on F4. So here we're showing the wiring connections for a high voltage connection and a low voltage connection. High voltage connection would be actually series in the field poles. You'd go out on F1, come back to F2, tie to F3, and then come back on F4. F1 is always going to be positive. A low voltage connection would be parallel connections for the coils. F1 and F3 are tied together and go out to each coil. F2 and F4 are tied together and go back to the negative side of the drive. One thing to remember, if the rating of the nameplate rating of a motor is based on single circuit amps. So this would be, if it's a 10 amp field, you'd have 10 amps flowing through this single circuit. If you wanted 10 amps through each circuit, you would have to supply with the motor with 20 amps of current. A compound motor series field magnetic polarity must be the same as the shunt field magnetic polarity for a cumulative compound DC motor. It's important that we correctly wire these so that this occurs. NEMA standard is that shunt winding is wired F1 positive and F2 negative. Rotation is determined by switching the armature, not the shunt field. The armature A1 is, in this case, for counterclockwise rotation, is wired to the positive side of the drive, and A2 comes back and ties to S1. S2 is always going back negative to the drive, and that's a rule to remember. F1 should always be positive, and S2 should always be negative back to the drive. All we're going to change when we change rotation of this motor is A1 and A2 connections only. And this would be the orientation of the wiring diagram, our wiring for a clockwise rotation. F1 is still positive, F2 is still negative, S2 is still negative, and all we've done is swap the A1 and A2 connections, where now A2 is positive back to the drive, and A1 is used to connect to S1 and then back S2 to negative the drive. Here's a typical DC motor nameplate. We'll go through some of these items on the name found on the nameplate. Horsepower is 250 horsepower. RPMs is 1150 and 1700. The 1150 is referring to the base speed. That would be with full armature voltage, full armature current, and full field current. 1700 is the top speed, which is full field weakening. It's a 500 volt armature rating. Armature amps is rated 398. It's a shunt wound motor. It's not got a series field. There's field amps, there's 8.2 and 4.75. The 8.2 is referring to the base speed amps. That's full field. We shouldn't exceed that. 4.75 is min field. That's at top speed. And the 4.75 is the minimum. We should not go below that. The field ohms is 21.4 at 25 degrees C, temperature corrected. It's talking about that's the resistance of a single circuit. In other words, if it was a dual voltage field, that would be with your coils in series. Insulation class is class F. The field voltage here is 240/120, so this is a dual voltage field motor. It does have F1, F2, F3, and F4. The 240 is the single circuit voltage, and the 120 would be the dual voltage circuit. And remember what we said, this rating right here in the amps is based on single circuit amps, not dual voltage, dual circuit. So if we had 240 volt applied in a series circuit, we would target 8.2 amps. If we were looking at 120 applied to parallel circuits, we would have to double that. It would be 16.4 amps from the drive out to the motor. Separately ventilated 590 CFM at 0.6265 inches of water pressure, inlet pressure, is how much airflow the motor needs for full rating and to clear carbon. So that's very important that we keep that amount of minimum airflow for both purposes, both for cooling and clearing carbon.